Hello, how y'all? Good. Y'all got quiet pretty good. Good evening. Welcome to the Baylor Research and Innovation Collaborative. The BRIC stands as the cornerstone of the Central Texas Technology and Research Park, and it's built around a unique paradigm that basically includes with one building research, both pure and applied, advanced workforce development, industry collaboration and partnership, incubation and acceleration through launch, and STEM education and outreach and research through Lex Labs. Each of these is important by themselves, but when combined within a single building, the results are generally pretty wonderful. The BRIC Foundation Speaker Series was actually established to bring world-class minds to Baylor from each of the 5 pillars that I just mentioned. This ensures, hopefully, that BRIC will continue to innovate across disciplinary boundaries, bringing to the forefront outstanding interdisciplinary and international partnerships. The inaugural speaker in this series was Dr. John Mather, who was awarded the Nobel Prize in Physics for his discovery of the cosmic background radiation. Since that time, we've had 5 additional speakers, each outstanding in their own right. Nick Ferris, Sector President of L3 Platform Systems and Division President of L3 Platform and Integration, followed John to discuss the connection between research and industry. Paul Evans, Director of R&D at Southwest Research, explained the necessity of a workforce to a successful research environment. Thomas Yerbukin, who holds the PhD in astrophysics and was a PI on the Messenger mission to Mercury, but also along the way became the founding director of the Center for Entrepreneurship at the University of Michigan and helped stand up their second billion-dollar company. Don't ask me, I don't know when he sleeps. Connected the dots between research, entrepreneurship, and business. Yuri Treisman, a foremost researcher in the teaching of mathematics, discussed the connection between research and STEM education and outreach. And our last person in this series was Fritz Schaefer, who's one of the most highly cited chemists in the world. For those of you who are geeks, his H-index is about 116. He discussed the connection between research and the political world. So today, we've got another august speaker who will bring the same level of expertise and wide-ranging interest to the table. Rob High is considered to be one of the world's leading experts in artificial intelligence and was named a research fellow at IBM in 2008 for his pioneering work in the field of service-oriented architecture and his leadership of the SOA Foundation. He's currently the Vice President and Chief Technology Officer for IBM Watson. He and his team are therefore responsible for leading the world in cognitive computing, supporting the development of deep natural language processes, and other cognitive computing capabilities in the areas of speech, language, vision, and reasoning. Under his leadership, IBM Watson is ushering in an entirely new era of computing in which systems interact with natural language, are able to analyze large volumes of unstructured data, respond to complex questions with evidence-based answers, and discover new actionable patterns and insights. Having spent the afternoon with Rob, I can absolutely guarantee you this is going to be fun. So please join me in welcoming Rob to Baylor.
Thank you, Trell, and thank you and Lori and everybody else who've done such a wonderful job today hosting us. It's been really a wonderful thing. I've had a lot of fun talking to, I don't know if any of you had a chance to meet with this afternoon, but whoever did, thank you for doing that. So let's talk a little bit about cognitive computing. I'm going to begin with IBM Watson. Now, how many here got a chance to see Watson play Jeopardy? Anybody? A few of you? Okay, good. Well, it's been about 6.5 years since that happened. And a lot's happened since then. In fact, 2 things in particular are pretty notable. One is we've just seen this explosion of the role of cognitive computing, AI, in our society, in our industries, and in the application of utility in things that we do on a daily basis. The other thing that's happened, actually more accurately, what hasn't happened is AI has not risen up and eradicated the human race. It hasn't, in fact, done a very good job of replacing humans at all, which is good, I think. But it's also important because notwithstanding some of the dystopian things that you see in Hollywood, or even some of the things that you might read into people like Elon Musk and others who talk about the concerns they have with AI, it actually is not our intent to replicate the human mind. Personally, I'm not even convinced that we're anywhere close to knowing how to do that. The thing I like for all of us to recognize is how incredibly complicated and sophisticated our human mind is. You know, we take it for granted. We don't think about the complexity that goes into the way that we think, the way that we perceive, the way that we reason, the way that we judge, the way that we decide how to conduct ourselves on an everyday basis. It's easy enough to kind of sit down and take a very simple example and discreetly break it up and say, well, here's all the logic that goes into, you know, a decision about whether to come here tonight or not. But that's really not representative of our human experience. Our human experience is much more sophisticated than that, much more nuanced, in fact, much more subconscious than that. So it's not inherently obvious that it's practically possible to replicate the human mind in general AI. But I think more importantly, it's not necessarily economically useful to replicate the human mind in AI. As I'd like to say, you know, there's 7.3 billion human beings in the world today. We got 7.3 billion human minds. And much more interesting ways of creating new ones that don't require us creating them in silicon. So, in fact, in as much as I'd like to point out how powerful the human mind is, it's also quite flawed. There's a lot of things that we don't do very well. I can read, I do that well, but I don't read millions of articles very well. And even if I could read millions of articles, trying to remember all that, trying to assimilate all that information, trying to make use of it, trying to recall it at the moment that we have to make decisions, doesn't work really well. So rather than trying to replicate the human mind, what we've been really trying to focus on is how to augment the human mind. How do we use cognitive computing to amplify our own human cognitive capabilities? How can we build systems that combine the power of our human mind with the power of a cognitive system to help us not just make better decisions? Clearly, that's one obvious utility that we can get from this. How can I make a better decision about what bike to buy or whether to come here tonight? But also to help inspire us, right? Because that is the one thing that we do really well, is we're creative people. We like to invent. We like to imagine. We like to come up with new ideas. That's fun, and we're good at it. The hard part is coming up with the ideas, getting in the right situation. I mean, think about the last great idea that you had. How did that happen? Did it happen because you were sitting, you know, in a room by yourself and somehow, you know, you just pushed the right buttons and suddenly a new idea popped in? No, it's probably because you just happened to be in the right room with the right set of people, with the right discussions going on, and in the right mood, and, you know, the right amount of alcohol. The right things to drink. The point is, these things tend to be very circumstantial, and the question becomes, can we make that more regular? Can we apply cognitive systems in a way that, on a more regular basis, inspires us, that helps us, you know, go through the process of thinking of the questions that we're not thinking to ask? That's our goal. That's what we're trying to do. That has a lot of economic utility. Another thing I'd like to think about here is, if you look at human history and examine the kinds of tools that we have produced. The tools that tend to have the greatest economic utility are the ones that extend our reach or amplify our strength. You know, hammers and shovels and hydraulics and levers and pulleys and all the other things that we have used to create buildings and cars and computing systems. Those tools that have lasted and had the greatest durability and viability and value to us are the ones that tend to amplify who we are, to extend who we are. And that is what we're trying to accomplish here with these cognitive systems. Now, we do describe cognitive systems around 4 major characteristics. Number 1, a cognitive system, if it's going to influence us, if it's going to have any kind of bearing on helping us make better decisions or inspiring us, it better understand us. It better understand at least our language. And by our language, I mean not just the written word, although obviously that's one main characteristic, but think about how we communicate with the world around us. You know, as you're listening to me right now, it's not just my words that you're listening to. You're understanding what I mean by mixing your understanding of the words, combined with my ability to inflect, to use vocalization with inflection and intonation and cadence and timbre to punctuate my words, to bring your attention to the words that I say that have more meaning or more importance to the things that I'm trying to convey. You're also influenced by my body language, my facial expression, my eye contact, you know, my arm and hand gestures, my body movement, my dorsal movements. You're influenced by all of these things. And so when you are communicating with each other and employing all these, the way that you're able to create an understanding is by people who are able to then look at all those things, hear all those things, see all those, or recognize all those different dimensions of communication. So when we talk about cognitive systems, we talk about systems that are able to employ all these devices and then to look underneath it all. Because oftentimes we don't say what we mean. Sometimes what we mean is more subtle than that. It's more inherent in the context in which we operate, in which we discuss things. You know, if my wife, you know, tells me that she's going to stop by the store on the way home, that's kind of an ambiguous statement, right? It doesn't say what store, exactly what time, what she's going to be doing, what she's going to be buying. But if she and I have had a conversation earlier about needing groceries for dinner tonight, I can use that contextual history to fill in the gaps, right? I know what time she gets off work. I know where she typically shops. I know that it's her turn to go to the store to get groceries. We all do this, right? It's our contextual history that allows us to communicate effectively in the presence of our ambiguous language, both contextual history as well as present context. In fact, something I will suggest to you as you listen to me tonight, think about how your own thinking is influenced, not just by what I'm communicating, but how much is influenced by the things that are going on around us. How much of your ability to understand me is predicated on the fact that we're all in the same room together, or that we're all sharing the same experience of that light coming through the window, or the noises that we hear outside, or the rumbling or the rustling of chairs and so forth. All of those are things that we are experiencing together, all of which is influencing how we think about and therefore understand each other in the environment that we're in. All of which, typically, for most of us, is pretty much in the background, right? If we're thinking about it at all, we're thinking about it subconsciously without a lot of conscious awareness. It's an important feature of how we communicate, but also an important attribute of a cognitive system and what distinguishes that from traditional computing. There are also systems that have to reason, and they have to be able to reason in a variety of ways, but specifically in whatever way allows it to draw conclusions that are meaningful and relevant to us. So if I ask a cognitive system a question, the answers that it comes up with needs to be relevant to the problem I'm trying to address. If it's going to inspire me, it has to inspire me in a space that I care about. It doesn't mean that it has to have the same logical processes that I would go through in my own mind. It doesn't have to replicate my own neural structure and pathways for reasoning. It just says that it has to reason in such a way that the result of that is relevant to the problems I'm trying to address, and hopefully, based on my earlier comment, in such a way that it causes me to be able to think about a problem differently than I might have if I were simply by myself, right? To be able to help me see through my biases, through my own limited perspectives, to see points of view that I might otherwise simply overlook, not think about, not consider. That's what a cognitive system should be doing. Now, I mentioned that there's different forms of reasoning. I want to kind of be a little bit more precise about that. The vast majority of examples of cognitive computing that you see out there today, and by that I mean very broadly, everything from, anybody here have iPhone, Siri, right? Siri to Amazon Echo to Google Home to whatever cognitive experience you've ever been exposed to, almost all of that has fit into a category of what we call inductive reasoning. If there's any reasoning at all behind these systems, the reasoning that's being performed is largely about trying to come up with answers to things that are already known, that have already been written down. They exist. The task, the cognitive reasoning task in all these systems is to, of all the things that are known, identify which of those is most likely to be the correct answer to the question you're asking. Or in the case of a command, the most likely interpretation of that command and the function that needs to be performed. What you don't find very much example of is deductive reasoning. I should take that back, because actually the entire history of modern computing is largely based on doing deductive reasoning around math problems. That's essentially what modern computing does, is it executes, mathematical, symbolic representations of math. I mean, that's what von Neumann was doing when he invented the computer back in 1947. The modern computer architecture, the von Neumann architecture, the very same architecture that we have on our laptops and our smartphones and in mainframes, that same architecture that von Neumann began with, he was formed around the idea that what we was trying to do was execute these mathematical models, these mathematical algorithms. When we talk about software is, programming languages are largely defined by representations of mathematical logic. So we do have that. And with that mathematical logic, we can deduce answers that weren't previously written down by executing the axioms of math. But that's, we honor math because we leverage it so heavily in our engineering and scientific disciplines. But math is actually not a very good representation of human experience. At best, it's an approximation of a model of experience. And in doing so, it can be highly precise when measured against that model, but it's not very accurate. Mathematical models tend not to continue to yield real-world results when they're exposed to things for which that model wasn't originally designed. And that's not useful if what we're trying to do is reason about a world that we all live in and augment our human cognition, which is largely a reflection of that human experience. So we need to be able to perform forms of reasoning that in the deductive space leverage axioms for which there isn't as much precision, symbolic representation, and yet still be relevant to the kinds of problems we're trying to deal with. Have you ever talked to a doctor about what logical path they went through to come to the conclusion about what diagnosis they're giving this patient or what tests performed to improve that diagnosis, and get them to explain the logic of why they chose that particular test or why they came to that particular conclusion, chances are, if they're really good at what they do, they can't explain it. They can't explain it because they've sort of assimilated it. They've buried the logic so deeply into their subconscious that it's almost intuitive for them. And that's kind of the nature of how our human mind is structured. The better we're at something, the less we understand it. So that's an area that I think you won't find very many examples of in the cognitive space. And the reason why I said what I said earlier about AIs that have not risen up, and why economically it's not interesting to think about AIs as a good replication of the human mind, is because they don't do this very well, because the task of capturing axioms of the things that are kind of interesting to us as human beings is really, really hard. And to generalize in that is even harder. There's another form of reasoning which turns out there's two subforms of, one of which we actually do quite well, what we call extractive abductive reasoning. So most of us who've been to school remember the days where we had to open up a textbook and there would be some information in that textbook about how to reason about a problem. In other words, the axioms of that problem space were documented in that textbook. That's the process of taking that information from the text and internalizing it is what we call extractive abductive reasoning. So that's pretty straightforward, right? If I can teach a cognitive system how to find facts in literature to perform inductive reasoning, then the task of extracting those axioms isn't that much more difficult. What is very difficult is what we call abstractive or abstract abductive reasoning. Coming up with those axioms, right? Who was the first person that figured out that 1 + 1 = 2? That axiom, we take for granted, we all know inherently, but yet somebody out there figured that out. And when they did, that was an abstract abduction that they performed. And we see lots of other examples of it in everything else that we do. So those are all aspects of reasoning that, on the one hand, defines a cognitive system, but on the other hand, and this is where you should take some comfort in where we are, we're barely down that path, right? We're only at the very beginning of the path of really capturing all those different forms of reasoning, and certainly not in a general form. Third thing is they have to learn. I mean, you can't sit there and write out all the rules that condition most of our human experiences. Think about all the little decisions you made on the way over here tonight. All right, I don't know how many of you drove, but if you drove, there was all of these decisions you had to make about, when to switch lanes and when to speed up and when to slow down and when to turn left and whatever. I mean, all these things that we just don't even think about, but yet nonetheless are these little decisions that we had to make, each of which have a set of rules associated with them, a bunch of conditions. And if we had to program these systems with all of those little rules, there would be millions and millions of them. I mean, that was just simply the task of driving here. Now take the task of talking, take the task of reading, take the task of interacting with people, take the task of learning a new topic. I mean, all of these things would require a whole new set of rules. And by the time we got capturing all those, either it would take us a very long time to capture them, but more importantly, by the time we got done, they'd have to change. They'd be, out of date. We'd learn something new that kind of change our understanding of whatever problem space we were dealing with, and then we'd have to write a whole new set of rules. So instead of programming these systems, we use machine learning techniques so we can kind of teach them. We can give them data that demonstrates the patterns that represent an understanding that when the system has seen enough of those examples, it begins to say, okay, wait, now I get it. I understand the difference between a bottle and a glass and a vase, all of which are cylinders that look like they're clear. Maybe they're made out of glass. They may all contain water. But that distinction is something that, through enough examples, we can teach a cognitive system to recognize. Which is another reason why, by the way, inductive reasoning is the most common thing that you see, because that's a form of recognition. Inductive is really a recognition process, and we know how to do that, right? That's what machine learning is really kind of enabling us to do. The fourth thing is they have to interact with us. And this kind of goes back to one of the things I've been hinting at here for a while in our discussion, which is that I can take the most intelligent person in the room, in the world, and put them in a room thinking about and reasoning about the most difficult problems that we face. But if that person, having done that, can't come out of that room and articulate the results of their reasoning, if they can't express it in a way that we understand, it kind of doesn't matter. I mean, think about how many times you judge whether somebody's intelligent or not by how well they articulate themselves, how well they express themselves, right? How quick are we to say somebody's stupid if they talk slowly, right? So cognition in humans is a function of both the cerebral aspects of our reasoning process as well as our ability to communicate, to express, to articulate, to interact with people in a way that's natural. And by the way, being natural is really key to being influenced. So go back to, again, 1947, von Neumann began work on the modern computer, and think about over the last 70 years or so, what has been our human-machine experience? And I think you'll find that mostly it's been defined by the constraints of the computer. Computer constraints are the thing that determines most what kind of interface we're going to have when interacting with it. Punch cards. Anybody had to deal with punch cards? Yeah. And then, TTY screens and green screens. And, even think about, our smartphones. I mean, think about the interface on this thing, right? Which is still largely about entering into text fields, slider buttons, radio buttons. We've learned to adapt to that because as humans, that's one of the things that we do well is adapt. But it's not natural. If I went home and started pushing my wife's buttons, you won't get the same effect. You've had that happen before? So it's time for us to think about these cognitive systems, differently. And because these cognitive systems are already, they're responsible for understanding us, they're reasoning in a way that's relevant to us, they're learning as they go, then we expect them to interact with us naturally as well, right? Through vocalization, through visualization, through physical expression. And that's going to make a big difference, and it's important to the very fundamental point, which is if I'm going to be influenced, if I'm going to be inspired to new ideas, it's not going to happen through a text interface. It's going to happen through sort of the psychological and emotional elements that bring that cognitive system into my presence, right? That creates a presence with me. And there's a lot of opportunity to advance in that space. All right. I'm just going to run through a few common concepts just because so many of my audiences end up being confused by some of the terms and jargon that you hear out there in the space. So starting with analytic systems. Cognitive systems are analytic systems. And you often hear them referred to as synonyms, but they're really not. Analytic systems, analytic algorithms have been around for even longer than computing has been around. Computers just became a convenient way of processing these algorithms. But these things have been around largely to do statistical analysis. And largely for the past 70 years or so in computing, we've been using computers to compute quantitative statistical analytics or analytic algorithms. So that's foundational, but it's not cognitive. It's not AI. It's important, but not sufficient. Natural language processing is another topic that's actually been around for a long time. The difference is that traditional natural language processing has been very fixated on the words and their meaning. So take a statement that somebody says, take each individual word, or maybe just a few of the words, and begin to look them up in a dictionary, and from that you can begin to process the meaning of that person's statement. That's been the theory behind it. The problem with that, of course, is that, again, that's not really how humans communicate. I mean, you don't go around with this big dictionary in your head, taking every word that I utter and trying to decipher its definition and then taking all those definitions together. You don't do that. That's not the way your mind works. You understand what I'm saying because of linguistics. And by linguistics, I mean word patterns. I mean punctuation. I mean distance. In fact, going back to Watson for Jeopardy, the reason Watson for Jeopardy was able to understand the questions that Alex Trebek was asking and answer those by looking up answers in literature was because it was focusing on features of linguistics, 130 different linguistic features in that system, right? And little subtle things that each by themselves might not have any kind of meaning, but together begin to create signals, and signals whose patterns now begin to represent meaning. That's how the cognitive system worked. That's how Watson for Jeopardy worked. That's really kind of the way that we work as human beings. Machine learning is sort of the statistical technique that we use that is both algorithmic, but more specifically is trained through data rather than having the precise algorithmic function or equation written out. We simply build matrices that are populated with data that then, through various algorithmic technique, begin to recognize the importance of signals and filter out the noise, separate the signal from the noise. And that's, a big advantage that machine learning brings to the table. Again, that's a technique that's been around for a long time. Cognitive systems employ these machine learning techniques not all by themselves. It's not like you can take a machine learning algorithm and say, okay, given the right set of data, now suddenly it's cognitive. Cognitive systems combine machine learning techniques. They use different algorithms under different circumstances and combine those, and merge those, and intersect them in ways that are relevant, that elevate it from simply doing a statistical analysis to now an analysis that's relevant in the context of something meaningful to humans. And then deep learning has become an re-emerging, I should say, statistical technique using biologically inspired neural nets. It's actually not a new technology. It's a technology that was started back in the 50s and 60s, got really big in the 80s, and then kind of died for a while there because it was economically not very interesting and hard to use, and you can never come up with enough data. But it resurged about 4 years ago. Renewed interest in deep learning algorithms. We employ deep learning extensively within our Watson cognitive systems. Has made a huge difference because oftentimes with a deep learning algorithm, you don't have to go in and engineer these features by hand. They kind of learn their own feature sets, which is really a huge advantage. Gives them a lot more adaptability. It also, unfortunately, requires a lot more data. But because of advances that have been made in hardware, in computational systems, we can do this reasonably economically now. And because of all that, it's just become a lot more interesting to use deep learning as a basis for our systems. And then the cognitive solution is one where we take all these elements, and usually variations of them, and combine them to go solve for a particular problem. In healthcare, we did this to solve for, and maybe some of you have seen this, there was a 60 Minutes episode on this not too long ago, where our oncology offering is helping doctors at UNC Medical School identify treatments for their oncology patients. Now, 90% of the time, the treatment options that Watson's identifying for those doctors is the same ones they would have come up with by themselves. But 10% of the time, it's coming up with a treatment option that they hadn't thought of. And that is huge, right? If you're an oncology patient, you don't want to be the 1 in 10 whose treatment recommendation was wrong. So that's an example of a cognitive solution. Now, what's driving this? Why is this suddenly becoming so interesting? It's not just because we did this great PR job at Jeopardy. And by the way, that wasn't intended just to be a PR activity. There was something really important that we were doing there. But nonetheless, the real reason why this has become so important is because of the amount of data that's being produced. Now, this is actually out of date. So these are 2016. These are numbers that are about a year old. But as of 2016, we were generating about 2.5 exabytes of data a day, every single day in our world. 2.5 billion characters of information being produced every single day. Anybody have a sense of how big that number is? This big. One way of putting it is that's about 625 billion Harry Potter books being written every day. Does that help? Still a lot. And it's growing. And again, this is out of date. As of last year, we estimated by 2020, 3 years from now, that would grow to about 44 zettabytes of data being produced every single day. It's actually bigger than that now. We estimate that to be about 160 zettabytes of data being produced every day in the next 3 years. It's more than most of us can read. Now, of course, not all of it's literature, right? I mean, a lot of it is literature. It's emails, it's papers, articles, books, stuff. A lot of it's actually quantitative data, right? The traditional thing, the substance of computing. A lot of it is recordings, right? This video stream is an example of adding to those 44 zettabytes. Audio recordings, of course, too. A lot of it is IoT data. Everything in our world is becoming instrumented. Everything that we touch, well, not everything, but a lot. My silverware still has not been instrumented yet, but I expect that to happen soon, right? And it's going to test the temperature of my food before I eat it, and it's going to check my saliva content for pathogens that might suggest that my health is bad, or so this stuff is being instrumented all over the place. This building, right, is heavily instrumented, I bet. That's generating a lot of data. And again, the question is, well, what do you do with all that data? How do you assimilate that? How do you make use of it? How does that data become something that is practically valuable to us? And since it's too big for humans to consume, we need help. And that's what's driving the need for these cognitive systems that can read and understand that data in all its different forms and come to conclusions that help us, and not make the decisions for us, but help us at least be better informed at the moment when we need to make decisions, or to help us think about the questions we haven't been thinking about at the time that we need those new ideas. That's what's driving this. Now, about 2013 or so, having done Watson for Jeopardy in 2011 and having decided to commercialize it and having had some early successes in the healthcare industry, this thing started getting really big. In fact, we realized this thing was bigger than us, that is IBM. This idea of cognitive computing and where it was going to go just got so big that, even today I get, requests for new ideas, for new solutions, right? These ideas come in. Can we use cognitive computing to go solve for this problem or that problem? And they're all fascinating and really important, interesting problems, but just bigger than we can handle as a company. So we made a decision in 2013 to pivot our business and shift towards a model where we kind of open up this cognitive technology and let other people build solutions. So we created a platform that really didn't get into its own until about 2015 and didn't really take off until about 2016, where instead of focusing our attention on solutions, we simply decompose the solutions into a set of building block services. and made the services available in the cloud through a set of APIs so that anybody can come in and build applications and solve for the problems that they care about. So most of my work since then has been about what are those building blocks and how do we advance them and how do we organize them in ways that have practical utility. And I started by sort of categorizing everything that we had done into three main areas. They're all in this purple layer, this layer in the middle that I call Platform as a Service, if you can't see that. And I took some inspiration from Daniel Kahneman, who's a psychologist, actually got a Nobel Prize in economics for some reason, but I guess psychology and economy goes hand in hand. Some of you may know that better than I do. Anyway, he kind of talks, if you ever read his book, The Slow and Fast Mind, he talks about System 1 and System 2. System 1 being largely representative or subconscious processes, which are largely responsible for recognition, reaction, that sort of thing. The things that we do quite well subconsciously, but although because it's subconscious we're not aware of, they're sophisticated, but they tend to be pretty primitive as well. And that's what I refer to as foundational cognitive skills. He also talks about System 2, which we can roughly equate to our conscious thought processes. And conscious thinking actually is, it requires cognitive energy. You can measure the number of calories we burn when we think consciously about a problem. Because typically when we're thinking consciously, we're evaluating trade-offs. We're looking at different ways of thinking about the problem. We're planning out how we're going to react to that problem or how we're going to articulate that. And all that takes energy. And that's what I call higher reasoning skills. And the third area, Kahneman doesn't talk about so much, but I think we're all familiar with, is the stuff that we do at night when we sleep, when we dream, right? It's the reorganizing our experiences of the day into information that's stored in our mind in a way that makes it easier to access later on. So I call that knowledge organization skills. And so those are the three main categories of services that we have in the platform, within which we have several services, and they vary. Now, the one that has the fewest number of services, but yet, for some of the same reasons I just mentioned, are the most expensive to perform, are these higher reasoning skills. Right now we have two of them. One is around conversational services, and the other is around discovery. Conversational services are how we go about articulating and expressing and interacting between machines and humans. Discovery is about how we reason deeply about a question or a problem that's being expressed and how we find answers or information that's relevant to that particular problem as expressed. That's what those two services do. Now, I want to focus a little bit on conversational services because, frankly, this is the thing you will see the most example of in our industry today, and not just by IBM, but really anybody who's kind of in this space. And you typically see them expressed in the form of chatbots, right? If you're familiar with Amazon Echo and Alexa skills, there's about 10,000 Alexa skills in the Alexa skill store. Siri, again, is another example of this, Google Home, et cetera. They're all kind of, we sometimes call them voice assistant agents. The thing about chatbots, well, first of all, what a chatbot does is it takes something that you utter vocally, or you could type, but it'll take whatever it is that you express, and it tries to understand your intention. It tries to classify your utterance. What is it that you intended to say when you said that? What did you mean by that? And if we're going to classify that, then I can map that onto a task or activity, right? So Siri, turn on the lights. Or Alexa, buy me new dog food. These are single utterance interactions that map an utterance classification onto a task. At some level, it's really pretty simple, even though the task of classifying is a fairly complex problem, but nonetheless, once you've done that, it's a pretty simple thing. The thing is that that's not the kind of conversations that we typically have with each other. Siri, turn on the lights is not going to yield very much inspiration. I'm not going to get a whole lot of new ideas out of that. we really need to kind of shift our mental model about these things and start to look for conversational systems that engage me. If I say, what's my balance? What's my account balance? Useful. If something can come back and tell me my account balance value, that's good. It's nice. But that's not my problem. Right? My problem is I'm trying to get ready to buy something. Trying to figure out whether I can send my kids to school. I'm trying to figure out whether I've got enough money in the account to go pay bills this month. There's something deeper behind that. And a conversational system should be about trying to get us to that deeper issue, to engage us in that. Because that's, from an institutional standpoint, from an enterprise standpoint, where the real value is going to be. Right? Your bank wants to offer you this service that gives you your account balance, not because they're a good citizen in life, but rather because they really want to engage you in financial services, right? You probably missed it, but that video essentially was of a conversational agent that began with a woman that got a fraud alert on her phone about a credit card transaction that looked suspicious. And it came up and said, is this a transaction that you authorized? Is this one that is legitimate? Is this one that you conducted? And in her case, she said, no, that's not. So, given that, the bank realizes it needs to get you a new credit card. So the conversation agent came back and said, well, we'll send you a new credit card. She came back and said, that's fine, but I'm getting ready to go out of town. So I can't wait the 2 weeks that it might take for the mail to get that credit card to me. Is there someplace locally that I can go pick it up at the branch office? Yes, of course we can do that. Let's arrange to do that. Where is that? Goes into a conversation about where the location of the bank is. But she just got done saying she's getting ready to go on a trip. Well, where are you going? Turns out she's going out of country. Well, if we're going to get you a new credit card and you're going out of country, we do have credit card products that have a better exchange rate, that handle foreign currency exchanges better. Let's get you one of those instead. By the way, why are you going out of town? Why are you going on this trip? Turns out she's going out on business. Well, we've got a corporate card that will save you money by consolidating some of your transactions, and we will treat you different with different rates because we know that what you're doing is business with this credit card. We expect that you're going to be using it more often for business expenses. Now you're into a deep engagement. That's a conversational system. That's a useful conversational system. That's one that is getting beyond what's my account balance kinds of questions. And that's what we not only think is valuable, but that's where things are going. That's what we're concentrating on. Now, to do that, of course, you have to have a conversation. You can't just simply have a back and forth of these sort of clinical statements. As human beings, we're emotional people, right? We, in fact, may go through an emotional arc over the course of that conversation. So a conversational system needs to somewhat be sensitive to that. It has to recognize our emotional tone. It has to understand something about who we are. It has to make decisions about what kinds of answers to provide given a question. Some of us, under certain circumstances, want very terse answers. Don't make me read a bunch of stuff. Just give me the answer. In other cases, I need to understand that better, get more elaborative. And how do we know when to do that with each other? Well, some of us aren't very good at it, but when we are good at it, we're picking up these little cues from each other, right? It may be the way that somebody said something. It may be contextual history. It may be a way that they reacted to us. And that's part of what the conversational system has to be sensitive to. And the other thing to realize is that, remember what I said earlier about it needs to be natural? What I just showed you is a fairly classic chat box-like interaction, right? I've got a chat box. It almost looks like a messaging interface. I'm typing in my statements. The system's coming back with responses back and forth and during this chat conversation. But that, again, is not necessarily natural. And that might be a little bit more natural if instead of typing I could speak. That might be nice. But it'd get really natural if I could both speak and it could see me. So I could speak through my facial expression. So the point to this is that very quickly, we're seeing a fairly massive transformation from, these smartphone-based apps, and this becoming, this has become sort of our primary point of interface to most of the systems we deal with. As we go forward, the point of interface is not going to be these. The point of interface is going to be the room we're in, the space that we're in, right? Whether that's our conference room, whether that's our office room, our hotel room, our cars, our homes. Where we are will become the primary point of interface. And what I'm going to show you here is a video of something that we did. It's a prototype that we have running live. This is a live system in our Yorktown Heights research organization, location, that kind of demonstrates that idea. This is two people in a conference room. They're trying to make a business decision about mergers and acquisitions. They're going to walk into the conference room and begin talking to the room. They'll be talking to each other, but they'll be talking to the room as well. The room will be interacting with them, and this is what the effect that we've created, but you can imagine how this is going to be applied to other cases as well. Oh yeah, we're not buying any of these companies. So I'm going to stop it there for the sake of time. But first of all, I should apologize. My engineers are not the best actors in the world. But the point is, what you should have seen in there is there was no keyboard, that you were interfacing with. It was all vocal. What you may not have picked up on is there's actually a camera in there, so Celia's actually looking at John and Jeff and picking up some of their facial expressions and gestures. There was a little bit of interaction. So the Celia was actually listening to them, and there's only one moment where he does this in this example, but where she recognizes there was something of interest. There was something about what they were talking about that Celia had information to offer, and offered. Is this what you're talking about? Can I present you the work that you guys were doing before? Is what you should have seen there. And that's just a small example of the kinds of human-machine interfaces that we're going to start to see starting to occur. We're already working with automobile manufacturers who want the car to kind of come alive to you when you get into the car, that recognizes you, and not only who you are, but who you're with, and what you're doing, and where you're going, and what's going on in the environment around you. When I go to work in the morning, I drive to work, I typically listen to NPR. Going in and back and forth. When I'm going down to Houston or up here, I like to listen to some blues. where I'm going changes what I like to listen to. It changes my mood. You know, if my wife is with me, we listen to whatever she wants to listen to. Yeah, exactly. You know, it's circumstantial, right? It's contextual. And so the car is beginning to adapt to and personalize not just on who I am, but what's going on around me. You know, if it's raining, does my mood tend to be different than it is when it's sunny? Do I tend to listen to something different? Do I prefer to drive in a different path? Do I have a different set of preferences in both the car configuration as well as how I get to places? If the car knows enough about me, my preferences, what's happening in the environment around me, what I'm doing, has access to my calendar, knows that, hey, I've got an appointment at 1, it's going to take me 30 minutes to get there, I haven't had lunch yet today, can it suggest to me places to eat along the way that I like, that would fit into my schedule? These are all capabilities that you're going to start seeing in these human-machine interfaces around conversational systems, right? Now, I mentioned we have these foundational cognitive skills. I'm not going to go through all these. As you may notice, we have the greatest number of services in the language space. That happens to be our tradition. That's where we started. That's what we've been focusing on the longest, so therefore you ought to see the greatest number of services there. But we've got capabilities in the speech recognition space. And this is not only just the ability to translate what somebody says, but to also begin to realize and understand some things about their inflection, and to be able to, when it speaks back, introduce inflection as a technique for conveying meaning and significance in the things that it's saying back to me. Visual recognition, world-class visual recognition service here that is not only able to identify what's in an image, but what's going on in an image, both a still image as well as a video image. And then lastly, I want to highlight empathy, right? Because again, if the cognitive system is going to have an influence on us, it better understand something about who we are, meaning our personality and how we're feeling. Now, there's a very subtle and important distinction between tone analysis and emotion analysis, right? Our emotion is intrinsic, right? It's how we're feeling inside. Tone is the emotional response we're trying to create externally in other people, right? How do we want other people to hear us, and what kind of reaction do we want them to have to that? So I'm going to talk a little bit about tone here for a moment. We have a tone analyzer that uses psycholinguistic analysis to predict how other people will hear what you're saying. What kind of emotion will they hear in what you're saying? And I took a dating service here as an example because, you know, in a dating service, I'm an online dating service, you'd like to believe that what people are putting down to describe themselves is reasonably positive. So you'd hope that that's how people would hear what they're writing. So I took this excerpt from a dating service profile. I'm not going to read the whole thing to you, but we can analyze that, and we can look at the entire thing, and we can recognize that a great deal of what has been said here, other people will hear with joy, which is good. I mean, that's what you want. But we can even do deeper analysis on this. So let's take this one statement. It says, what I'm doing with my life, working toward a new goal, keeping fit, helping others, and traveling whenever I get a chance. And again, you know, most people will hear joy in that. I think it got clipped out here, sorry, but most people will hear joy in that, and that's good. Let's take a slightly different example. I'm really good at listening, enjoying the moment, and many other things. Turns out 21% of the people will hear sadness in that. Right? Why? Well, I'm really good at listening, enjoying the moment, and many other things that I'm just too depressed to tell you about. It tapers off, right? It just trails. It doesn't elaborate. It doesn't go on and kind of complete the thought of what I enjoy. If I enjoy life, there ought to be excited. There ought to be a lot of things I want to talk about that are joyful. And if I don't, people start to hear sadness in that. Take another example. I raised 2 great kids, and now I'm starting a new chapter in my life. 23% of people will hear anger in that. I raised 2 great kids, and damn it, I'm starting all over again. She took all my money. Well, it's a new chapter in my life. It's a positive thing there. The point is that how we speak how we speak, how we write, influences how people will hear us. Be the same words, but when ordered or structured in certain ways, people will begin to read into that, and that influences people. We're influenced by that. Now, of course, one way of thinking about using this is like a spell checker, right? Wouldn't you like to be able to, tone check just before you send that note off to your boss? How are they going to hear this? Are they going to hear it the same way I intended for them to? And we've talked to people in marketing who want to be able to do this sort of thing before sending that marketing message out to, communication out to your customers. Let's make sure we understand how they're going to respond to that. But we use it within conversational systems, again, to affect and influence the interaction. So I'm going to show you one more video here. In this particular case, I'm taking the exact same scenario, and I'm going to run through it twice. In the first case, JJ is going to be very positive. And Watson's going to pick up on sort of the positiveness in his intonations. And we'll take the conversation in one direction. And then you're going to see the same thing again. And this time he's going to be deliberately very negative, and Watson will pick up on that and take the conversation in a slightly different direction. And don't be distracted. This is done through a robotic interface, but this is not about the robot. This is about So you see here how cognitive system, by being able to pick up on that intonation, the tone of expression, is able to use that to guide the conversation, in this case being a little bit more conciliatory when JJ is being negative. And that's important. That's an important aspect of how we're going to achieve conversational systems that have real impact on people. So I'm going to end there because I've already gone over my time anyway, but I also want to kind of give you guys a chance to ask questions if you had any. So let me stop there. Yep.
Probably very expensive in terms of processing power. How long till it's more commodity?
Let me answer that in two ways. First of all the things that you saw me list under higher reasoning skills, foundational cognitive skills, and I didn't list the knowledge organization skills, all of those are available today as APIs in the cloud for anybody to use. You can, right now, when you go home, log into ibm.com/bluemix, create an account, and get access to those services, and they're free for you to use for 30 days. And then if you want to get a subscription to use it longer than that, it's actually quite cheap. You'll be surprised at how cheap it is. We make our money on volume, right? So it's not to say that there isn't a lot of computational power behind it, but on an individual basis, it's really quite cheap. So that's where we are with that set of services. I also want to kind of answer this a different way, which is, as I sort of hinted at or indicated earlier, we're about 70 years into modern computing. Since 1947. We're just now beginning this new era of computing called cognitive computing or AI that I think is going to take us another 70 years. Right? We're just at the very beginning of what's going to turn out to be a long period of time of evolving, advancing, maturing, applying these cognitive AI technologies to solve a whole range of problems. And I'll remind you, right? Think back 10 years ago to what your life was like before this thing came along and how different it is now. We're going to, and I don't know that anybody knew back then, 10 years ago, how profoundly this would affect us, right? That, I can't go anywhere. I mean, this sits by my bedside at night when I go to bed. It's the last thing that well, I said goodbye to my wife first, but, say goodnight to her, and then, then I might shut this thing down, and then the first thing I wake up in the morning, I turn that on to see what's going on, and then I say hello to my wife again. That's how profound it is. And we didn't predict that 10 years ago. And I think the same thing's going to happen here with cognitive systems. We can't predict what's going to happen over the next 10 years, but I can tell you it's going to be profound. But I also think that it's just beginning. Even in 10 years, that's just the first 10% of everything that we're going to see coming out.
What do cloud computing corporations like IBM and other corporations who deal with large amounts of data, how do they kind of poise themselves as ethical watchdogs? And
excellent question. Yeah.
How much privacy do y'all give y'all's clients? How closely do y'all monitor their use of y'all's tools and services?
So we pride ourselves and differentiate ourselves on data privacy. Our business model is quite a bit different than the other cloud providers out there. Certainly, Google and Amazon, most of their revenue is generated off of things like, in the case of Google, knowing something about you and being able to sell that. Advertising. In the case of Amazon, they actually use some of that to drive some of their decisioning within their retail space. We don't have any other way of making money other than by you using our cloud. So we protect your data. That's sacred for us, is to protect that data. Now, that's not to say they're unethical about it. I'm not suggesting that Amazon and Google are unethical, but we absolutely focus on, look, if you're going to do a subscription with us and you're going to put your data in there, that's your data. We don't have access to it. We don't use it. We don't use it for any other reason. We do look at one aspect of what you do, which is when you're on our cloud, we watch to see how you are interacting with other outside entities for patterns that might suggest that you are a rogue that is using our servers to go attack other people, right? So if you're using our servers as a base for hijacking data, we don't see the data, but we can tell from the patterns of interaction whether you're polling somebody with a virus and things like that, right? So we do monitor for that without looking at your data, but just simply looking at the patterns of interaction that occurs between us and whoever else you're interacting with. And that's really to protect everybody else that's on the cloud with us, right? So that they're not, being affected by rogue institutions that may have, taken over our cloud system. Ethics are a really important issue for us right now. And that is because, like anything that has the potential to grow the way that we predict it will, it's better to start thinking about the ethical aspects of that technology sooner than later, at its very beginning, if you can. And so for that reason, we formed a partnership with a number of other vendors called the Partnership for AI, whose purpose is to begin establishing ethical guidelines. And we've already begun to practice that. For example, whenever any of our clients come to us and want to build a conversational system, number one rule, don't build a conversational system that pretends to be a human being, right? End users of these conversational systems should never be fooled into believing that who they're interacting with is a human being. Why? Because we, as human beings, behave differently when we think who we're dealing with is a human being. Our trust assumptions change. So, that's an ethical rule that we've established with that organization. I don't want to be in a situation where, Teller was in right after having helped, invent the atomic bomb and suddenly worry about what people are going to do with that. I don't want to be in that situation. Nobody in my business wants to be in that position. And so now's the time to start looking at that and thinking about that. And I won't say that Elon and Hawkins and these other people who are raising alarms are wrong, because if there's anything that is important about what they're saying, it is that we ought to be thinking about this stuff now. And I'd say we here to mean not only us as providers of technology, but also consumers of that technology, meaning the developers who are creating applications using it, as well as the end users that are exposed to that technology. All of us have a role in this. And all of us will be better off when all of us are thinking about our own responsibilities in that space. And now's the time to do it. Yeah.
Your grandson, what and how should we be teaching our children in school?
He will teach you, he or she. Yeah, he will be teaching you. You know, I watch my own kids, right, with these things. They know more about how to use this than I ever will. You know, I couldn't teach them. They taught me. I think the same thing's going to happen here. But that said, go back to the ethical question, they have a responsibility. My kids are so cavalier when it comes to using systems on the internet about giving away their data. I'm constantly chasing them. Why did you give them that information? That's something that I think we can all help them, this next generation with, is be more sensitive and conscious of their own identity and the information that they ought to be providing to support the things they want to do. You don't have to be giving away all your information to do that. Look, I mean, these kids are amazing to me, and their ability to adapt and assimilate new technologies. The younger they are, the sooner they get exposed to it, the faster they're going to pick up on it. And they'll pick up on it in ways that we who have been around for a while, those of us who remember punch cards, we will be always much slower than they are at adapting this stuff. Anything else?
I was intrigued early on in your conversation. You talked about the hope is better decision making.
Yeah.
And most of your examples have been individual decisions.
Mm-hmm.
But we see an awful lot of what seem to be terrible decisions being made.
Mm-hmm.
The world is doing some crazy things. Is there anybody trying to use this, that scale of political thinking? I mean, there's so many ways you can make a choice that seems right, but it's almost beyond human comprehension, all the ramifications, and then end up in places you never want to be.
The answer is yes, people have. I mean, if you want to talk about elections, elections now are largely a quantitative problem. They're an analytic problem. So it's already being used there for that. There are, well, let me put it this way. If you don't use the technology, you're not going to benefit from it. If you use the technology in a way that abuses it, you're not going to benefit from it. So a little bit it has to do with the user. But yeah, there's lots of examples. The one I gave earlier about oncologists now making better decisions about treatment options. Again, go back to that episode on 60 Minutes, and you'll see how these oncologists, who are experts in their field, they do this every single day, still see the benefit of having a system that, even if all it's doing is 10% of the time giving them an answer they hadn't thought about, is 10% of the time that they're now getting answers that they wouldn't have come up with by themselves. So, yeah. At a more macro level, I think that we'll see more of that. Some of it has to do with what applications have been created to support these kinds of decisions, what the decisions are. And by the way, don't be misled into anything that I said to mean that Watson works by you just simply dumping a bunch of information into it and it magically coming back with this insight. It's not omniscient. It's not sentient. But it certainly will provide you information that you might not have expected, and that can be very useful in making those decisions. All right, guys, let's. Oh, yeah, no, go ahead. Yeah.
Can you talk a little bit about subtlety in language and how you can teach a robot like things like sarcasm or how to tell if somebody's lying? Is that a capability that you can train?
In theory, yes. We haven't. Remember, this is all about collecting signals and looking for patterns of signal that represent meaning. And if part of the meaning that you're looking for is sarcasm, yeah, certainly you can train a system to look at those signals in that light, or lying. In fact, we've had some work going on with RPI, Rensselaer Polytech in New York, around fake news, which is part a linguistic problem. It's also about a source problem, veracity and. But yeah, absolutely, yeah. Yes.
Yes, I have a question. So whenever it comes to cognitive systems and stuff, I'm going to assume it takes a cornucopia of computing power and stuff in order to run these systems. Whenever it comes to quantum computers and stuff, even though they don't exist yet, there's no proof that they cannot exist. And from what I was able to read up on, they're able to do like processes and stuff in like a grand amount of parallelization and like logic blocks and stuff in the architecture of the processor if it was to exist. They can like move around and stuff, like move around the logic blocks. Well, how could that like be applied to cognitive computing and things like general artificial intelligence? And if general artificial intelligence is to exist, how quickly could it go into superintelligence?
So you've said several things that I want to respond to. First of all, that runs cognitive computing on it. Siri, doing voice recognition or facial recognition, is running on an A6 chip, or I forget what this A6 or A7, whatever it is in it. So it can be quite small from an inferencing. What typically takes so much computational power isn't the inferencing, it's the training. And even that is getting more efficient. We're doing a lot of work with the power team on optimizing architectures for doing training even more efficiently. So it doesn't have to be, would you say cornucopia? Cornucopia, I guess that means a lot, right? It doesn't have to be a lot of compute power depending on what the problem is you're trying to solve. That said, quantum computers do exist. In fact, we have a 5-qubit system that is open for anybody to use up in Yorktown. It's on the web. You can go sign up and get, for the right amount of effort, get time on the qubit system, the quantum computer we have up and running. And those are going to get faster. I have not figured out myself how best to exploit quantum computing to benefit cognitive computing. I have a strong intuition that it will, if for no other reasons than what you were suggesting, which is that somehow it's going to give me the throughput that I need to be able to compute these models faster. But I don't know how yet, and we just haven't done enough to figure that out. I don't think there's anything magical about quantum computing that applies to general AI. Again, I haven't spent much time thinking about it either, so I could be wrong about that, but I don't see anything obvious that would suggest that quantum computing is going to somehow turn the dime on getting to general AI. I think the issue with general AI is utility. As I said earlier, I just don't see a whole lot of economic value in replicating the human mind in computing. Some aspects of the human mind, the way that we reason or the kinds of reasoning that we perform, that by itself has utility. But, what value is a system that has, sentience or its own ability to be creative really going to bring to things, to a world which is already heavily populated by people who are really pretty good at it? That's the one thing that we really do well. So I don't see a real strong correlation between quantum computing and general AI. All right, guys, look, I'm way over time, so I'm going to stop here. Thank you very much for having me here today. I got water. What else do I need? Oh, well, thank you so much. Thank you.
Thanks very much. Appreciate
Brown
it.
paper
Very
bag. Thank you,
excellent.
everybody. Thank you.
Thanks a lot. Appreciate it.
Yeah.
That's great. Anytime you want to come down.